Okay, you guys, let's get to writing formulas for ionic compounds without having to draw out Lewis dot diagrams for them. So you're going to need your periodic tables handy, and you need to remember what we learned about how to predict the ionic charge of different elements. Okay, so we're going to start with binary compounds. Binary compounds are really simple. They are composed of only two elements. In other words, the ions in the compound are always going to be monatomic. Okay, so these are composed of only monatomic ions, not the polyatomic ions that we talked about in our introductory lecture. Okay, so let's say that I wanted to create a compound between sodium and chlorine without having to draw those Lewis dot structures. All I need to do is find sodium on the periodic table. Sodium's in group 1, and so sodium will always make a 1 plus charge. And then I'm going to find chlorine on the periodic table, and chlorine's in group 7, which means chlorine is always going to make a 1 minus charge. And then I need to make those charges cancel one another out. In other words, to have a stable ionic compound, the charges have to net out to 0. And we know that a 1 plus and a 1 minus will cancel one another out. So I only need 1 sodium and 1 chlorine. And I show that formula for the compound as NaCl, just like we did when we were drawing Lewis dot diagrams. Remember, we use subscripts to show how many of each ion are in the compound. But if that subscript is a 1, we omit it. Okay, so 1s are understood. So if I wanted to sort of like think about a little thought process, you write the cation and the charge, and then you write the anion and the charge, and then you make those charges cancel by adding subscripts. Now, we'll also start talking about the names for these compounds. When we go to name the formula, we name the cation first. Just like we write the cation first in the formula, we also name the cation first in the name. And so that cation is sodium. And then we name the anion, but we change the anion ending to "ide." Okay, so for monatomic anions, we change the ending to "ide." So that is sodium chloride. Let's do another one. Let's say we wanted to make a compound like on our worksheet that we did the other day with magnesium and fluorine. Find magnesium on the periodic table. It's in group 2, so it makes a 2 plus charge. If I want to bond that to fluorine, which is in group 7, which always makes a 1 minus charge, now I need to make those ions charges cancel out. So in order to do that, I'm going to need 2 of these fluoride ions because they each have a 1 minus charge. So to cancel out a 2 plus, I need 2 of these 1 minuses. So of course we show that with a subscript, MgF2. Voila. It's the same formula we came up with by drawing the Lewis dot diagram, but we don't have to do it. All we got to do is write the ion and the charge, the ion and the charge, and make those charges cancel with multiples of each ion written as a subscript. Go to write the name of the cation first, magnesium, and the anion second. That's the element fluorine, but I'm going to change the ending to "ide." All right, let's do one we haven't seen yet. Let's do strontium. Strontium is in group 2, so it's going to have a 2 plus charge. And let's do, how about nitrogen, which is in group 5. In group 5, remember they gain 3 electrons to get to 8, so a 3 minus charge. Now I want these charges to cancel each other out. And in order to cancel out, we need the least common multiple between a 2 plus and a 3 minus. And that least common multiple is 6. So I need to make the total positive charge 6 plus. And I need to make the total negative charge 6 minus. So I'm going to do that with subscripts. Strontium, need 3 of them because 3 times that 2 plus charge will give me a 6 plus. And my nitrogen, I'm going to need 2 of them because 2 times that 3 minus charge will give me a total of 6 minus. And if I want to name this ionic compound, all I have to do is name my cation. Don't change its name in any way. This is strontium. Change the ending of your anion, which is nitrogen, to nitride. Okay, should we do one more? Let's say I wanted to write the formula for a compound between aluminum. Aluminum's in group 3, so it's got a 3 plus charge. And let's say bromine. Bromine is in group 7, so it's going to make a 1 minus charge. I'm going to make those charges cancel out. I'm going to need 3 total bromines to get to a 3 minus overall. AlBr3. And the name, aluminum bromide. Oh, look, my handwriting's getting a little better. Okay, so this is how we write names over here and formulas for ionic compounds. All right, let's get a little bit more complicated. Remember how when we were predicting ionic charge, I said that the transition metals will have Roman numerals in their names to indicate their charge. Let's do a couple of example problems utilizing transition metals. Oops, scrolled a little too far. Sorry about that. Okay, so remember the Roman numeral in the name equals the positive charge on the cation. So this time, let's practice going from a name to a formula. Up above, we were writing their formulas first and then getting the names. Let's go in reverse this time. Let's say that I give you the name iron, Roman numeral 2, oxide. We're going to do the same thought process as we did above. We're going to write the ion and the charge that it makes, and then the other ion and the charge that it makes, and we're going to cancel those charges out. So, what's my cation? Iron. Can't figure out the charge by looking at the periodic table because it's a transition metal. So I need to use the Roman numeral given in the name. Iron 2 plus. And now I'm going to write my anion, oxide, that's oxygen. And oxygen makes a 2 minus. So to make those charges cancel out, I only need 1 of each. And again, 1s are understood, so I'm not going to use any subscripts. There's my formula for iron 2 oxide. Let's do another one. Let's say instead of iron 2, let's say this time I have iron 3. These transition metals can have varying different charges. Let's say this one is iron 3 oxide. These are 2 different compounds. Write the ion and the charge that it makes. 3, oops, that is not a 3. Iron 3 plus. And we know oxide from before is O2 minus. I need to get those charges to cancel out. So my least common multiple is 6. I'm going to need 3, nope, I'm going to need 2. I keep confusing my 2s and 3s. I'm going to need 2 iron cations to get to a 6+. And I'm going to need 3 oxide anions to get to a 6-. So that is how we use the transition metals in order to write the formulas of those ionic compounds. You have to just pay attention to the Roman numeral that is given in the name. Okay, now let's do a couple of transition metal examples where I give you the formula and you have to come up with the name. These are a little bit trickier. Let's say I give you the formula CuS. If I ask you to come up with a name for this, you would write the cation name just like we did up above. However, we need to incorporate the Roman numeral. And then I name my anion sulfide. Okay, so just like we did in these problems up here, where it's just simply name the cation, name the anion, change it to -ide. Name the cation, name the anion, change it to -ide. You get the picture, right? Name the cation, name the anion, change it to -ide. We're doing the same exact thing down here. We're naming the cation, we're naming the anion, and we're changing the ending to -ide. However, we have to include the Roman numeral that tells us the charge on the copper, because copper is a transition metal. The way that we figure that out is we simply work backwards from the charge on the anion, because sulfur, the charge on sulfur is always a 2-. So if I know that sulfur is a 2-, the copper has to cancel that 2- charge out. And so in this case, copper is going to be a 2+. And so my Roman numeral in my name is copper 2. This is copper 2 sulfide. However, what if I gave you the formula Cu2S? This is a different compound. Again, it's going to be copper. It's going to have a Roman numeral, and the name is going to end with sulfide. However, the charge is different this time. Again, let's work backwards. Sulfur over here has a 2- charge, which means that the copper in this case has to have a 1+ charge, because there's 2 of them that are being used to balance out that sulfur 2-. So in this case, this is an example of copper with a 1+ charge. This is copper 1 sulfide. Let's do one more example where we're working backwards from a formula to a name when we have transition metals in the mix. Let's say, I need a good example here. Let's say I have nickel. That's what happens when I have to make up things on the fly. And nickel and oxygen. Okay, now I'm ready. All right, so I'm going to write my cation name, nickel, and I'm going to wait and figure out that Roman numeral in a little bit. And then I've got my oxygen, so I'm going to change the name to oxide. I just realized that I've picked oxygen and sulfur for all of these examples. That's okay. The thought process is what matters. All right, let's work backwards to figure out the charge on the nickel. I know that oxygen, because it's in group 6, always has a 2- charge. But here I'm going to have to do a little bit of math. The other ones I could kind of do in my head. Here, if I have 3 oxygens, each with a 2- charge, that is a total negative charge of 6-, which means that the nickel needs to have a total positive charge of 6+. However, there are 2 nickel atoms making up that 6+ charge, which means that each individual nickel ion must have a 3+ charge. So I kind of worked backwards, right? You always know the charge on the anion. You figure out what the total negative charge is. The positive charge has to be equal and opposite. And then you look at how many atoms are making up that charge. So you can, if you work backwards in that little logical box, or maybe you could just do it in your head, you could see that this is nickel 3 oxide. Okay. Now, there are 2 transition metals that do not have Roman numerals in their names because their charges are always the same. And that is zinc, always has a 2+ charge, always. So you're not going to see a Roman numeral for zinc. And silver always has a 1+ charge. So you're not going to see Roman numerals in the name for silver either. Probably should have talked about that when we were labeling our charges on our periodic tables. Maybe you guys could go back to your periodic tables and circle zinc and circle silver. They will always be 2+ and 1+ respectively. Okay. Now, let's complicate this even more. Although it's the same thought process, you guys, so don't get scared. Let's start writing formulas for compounds that include polyatomic ions. And if you remember back to our intro lecture, a polyatomic ion is a bonded group of atoms with charge, and they've got special names and special formulas. So remember some examples of polyatomic ions, and you've hopefully printed your polyatomic ion sheets out. Some examples would be like NH4 with a 1+ charge. That's ammonium. Or SO3 with a 2- charge. That is sulfite. Or OH with a 1- charge. That's hydroxide. There's tons of these, and I only want you guys to learn and memorize that list that I gave you. Okay, so when we have these polyatomic ions also in the mix in our ionic formulas, we end up with things called ternary compounds, and these contain 3 or more elements. So if we look up above to all of these other examples we've been doing here, you can see that all of these formulas only contained 2 elements, like nickel and oxygen, copper and sulfur, or aluminum and bromine, and strontium and nitrogen. They only contain 2 elements, so we call those binary. When we have these polyatomic ions bonding, now we're going to end up with more than 2 elements in our compound. You'll see. Let's say I want to make a compound between sodium and this polyatomic ion up here, sulfite. Well, maybe I'll just give you the name, right? We'll go from a name to a formula. Sodium sulfite. Follow our normal rules. Write the cation, sodium, and the charge that it makes. Now write the anion, SO3, and the charge that it makes. The reason why I know that sulfite was SO3 2- was because I just learned my polyatomic ions and memorized them. But the other key is that the ending of the name is "ite." If I was talking about just the element sulfur, I would name the ending, or I would change the ending to "ide." Okay, so if it ends in "ide," it's talking about the element. If the name ends in "ate" or "ite," it's referring to the polyatomic ion. Okay, Now, there are a couple of polyatomic ions that also end in "ide," but we'll talk about that a little bit later. Okay, so back to writing my formula. I wrote my cation and the charge, I wrote my anion and the charge, and now I need to make those charges cancel out. A 2 minus and a 1 plus. I'm going to need 2 sodiums. I need 2 of those to get to a total of 2 plus. And that will cancel with the 2 minus on my sulfite. Notice I have no charges in my final formula. Okay, so this work that we're doing over here that we've been doing all along, make sure those charges cancel and do not include charge in your final formula. Let's do another one. Let's say I want to make a compound between ammonium and, how about this? How about nitride? Ammonium nitride. Write the cation and the charge that it makes. If you went looking for the element ammonium on the periodic table, you're not going to find it because it's not an element. It's a polyatomic ion. It's this NH41+. And the next ion is nitride. Remember, if it ends in "ide," it's the element with only 2 exceptions. Okay, so nitride is the element nitrogen. Nitrogen's in group 5, so it makes a 3 minus charge. So now I need to cancel out this 3 minus with this 1 plus. And so I'm going to need 3 of these ammoniums. Now, the way that we show that with the polyatomic ions is with parentheses. So I have to put the parentheses around my polyatomic ion so that I can say I'm going to need 3 of them. And there's my 1 nitrogen. If I didn't put those parentheses there, you guys, it would look like I had NH43. That's not what I have. I don't have 43 hydrogens. I have 3 of the unit NH4. Okay, so we are going to use parentheses around polyatomic ions when there's more than one of them. Here, I did not need the parentheses around the sulfite because I was only using 1 sulfite. But if you want to put those parentheses around there because it makes you feel better, that's fine. But you're not going to see me do that, and you're certainly not going to see that in any textbook or on any chemical bottles. All right, let's do another one. Let's say I wanted to make lithium hydroxide. Lithium is in group 1 and makes a 1 plus charge. Now, here's a tricky one. Like I said, normally when it ends in "ide," we're referring to the element. But there's no element, you guys, called hydroxygen. Okay? Hydroxide is this polyatomic ion. It's this OH1 minus. Okay? So OH1 minus. Oh, look, a 1 plus and a 1 minus just already cancel each other out. I only need 1 of each. Let's get really fancy. Let's do a transition metal and a polyatomic ion all together. Okay, what transition metal should we use? Let's say, it would be helpful if I had a periodic table handy, so I'm not trying to like imagine things up all the time. Let's say I'm using chromium. Roman numeral 3. And the polyatomic ion sulfate. So yes, there's such a thing as sulfite, and there's such a thing as sulfate. Okay, write the ion, chromium, and the charge that it makes. The Roman numeral tells me it's going to be a 3 plus. Sulfate Go look on your polyatomic ion list that you printed out, or maybe you've already memorized them. Sulfate is SO4. Whole thing has a 2- charge. I need to balance out a 3+ with a 2-. So I need to get to a 6+ and a 6-. That's my least common multiple. So to get there, I'm going to need 2 of my chromiums, and I'm going to need 3 of my sulfates. Notice how we never mess with the subscript within the polyatomic ion itself, okay? You're never going to change that subscript. That is like a little unit that you can't mess with, and it has a 2- charge. So to get to a 6- overall, I got to put my 3 on the outside of the parentheses. Okay, good job. You now know how to write formulas for substances that include polyatomic ions. And let's just highlight one thing really quickly here about these names when we're referring to polyatomic ions. If I gave you the ending sulfide, any name, something sulfide, if it ends in "ide," it's referring to the element sulfur with its charge. If I gave you the name sulfate, it's referring to one of the polyatomic ions, and you just have to learn them. That's sulfate. Okay, so if it ends in "ate," polyatomic. There's also a polyatomic version that ends in "ite." Sulfite, SO3, 2-. Okay, so if it ends in "ide," it's referring, and again, these are, anion names. Okay, so you're going to have cation, anion, cation, anion, cation, anion. And this first one is referring to an element because it's ending in "ide. And these two, because they're ending in "ate" and "ite, are the polyatomic ions with sulfur in them. And unfortunately, there are 2 polyatomic ions that end in "ide, and those are hydroxide and cyanide. But most of the time, if it ends in "ide, it's talking about the element. Okay. Should we summarize all of those rules into one nice, neat, easy little chart? Let's see if I can write small enough to fit in here. I probably should have copied and pasted over a bigger chart. Okay, writing ionic compound formulas. Here's what we do. We simply write the cation symbol and the charge. So we write the cation with its charge, and then we write the anion with its charge. So you write your cation with its positive charge and your anion with its negative charge. And then you balance charges. How do we balance the charges? We balance charges by using subscripts. And once we use those subscripts, those charges cancel out, and so there will be no charges in the final formula. My handwriting looks terrible in these tiny little boxes. I'm sorry, you guys. I'll get better. Okay. Now, that's how we write the formula. So let's do one final example. Oh, you know what? We'll wait until we have the naming rules, and then we'll do one final example. Okay. Writing ionic compound names. You're going to name the anion. No, gosh, why did I say that? You're going to name the cation. Cations always come first. Silly. So you name the cation, and you don't change the cation name in any way, right? It's either just sodium or aluminum or lithium or zinc. The only time you have to do anything funny with the cations is sometimes you need parentheses with a Roman numeral in there for your transition metals. Okay, so if your cation is a transition metal, you're going to need to use that Roman numeral in the name. And then you name the anion. If your anion is an element, you're going to change that ending to "ide." If the anion is one of your polyatomic ions, you're simply just going to name it. You just have to learn the names of your polyatomic ions. Sometimes they end in "ate." Sometimes they end in "ite." And unfortunately, sometimes they end in "ide," because elements always end in "ide." But the only polyatomic ions that you need to know that end in "ide are OH-, that's hydroxide, and CN-, that's cyanide. Oopsies, I went off screen, didn't I? You guys can't see my cyanide. There we go. Okay. So I know that was a lot. Please, come to Extra Help. We'll do lots of problems together where we practice writing names and formulas. And I said I was going to do one last example, so here we go. Let's say I gave you the formula ZnCl2. There's my formula. Rules for writing my name would be name the cation. The cation is zinc. If it is a transition metal, I'm going to need a Roman numeral in the name. Zinc is a transition metal, so you would be tempted to put a Roman numeral in here for the charge. But remember, I told you zinc is always a 2+. That's one of the exceptions. So I don't need a Roman numeral. And then I'm going to name the anion. And because that's an element, I change its ending to "ide." That's zinc chloride. Okay? And let's do one more where I give you a name and you have to write the formula. Let's say I give you the name manganese. One phosphate. So there's your name. We're going to follow these rules to write the formula. First, we write the cation and the charge that it makes. Manganese, and I was given a Roman numeral, so that means a 1+. And then I write the anion, phosphate. If it ends in 8, I'm going to have to go look that thing up on my polyatomic ion list. I mean, I don't have to because I've got them memorized, and you will too soon. Okay, phosphate is PO4 with a total charge of 3-. Now I got to make those charges balance out by using subscripts. How do I balance out a 1+ with a 3-? I need 3 of them. Mn3, and only 1 phosphate is needed. So I just write phosphate, PO4. Okay, so that 4 doesn't mean 4 phosphates, right? That 4 is part of the phosphate polyatomic ion. All right, you guys, good job. I'll see you in class.